بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Welcome everyone to the third lecture. First of all, you've seen the announcement, so that's why you're in this new room. You've also seen the homework. Who did the homework? Okay, good number. Any problems that you faced during the homework? Easy? Okay. For those who didn't do the homework, again, so every week, inshallah, every maybe a couple of weeks, I'll try to put these homeworks so that you can practice the concepts that were discussed in the lecture. We usually give some examples, but not too much, okay? Otherwise, it will be too detailed, and usually the concepts might confuse you and not help you. But the abstract concept is abstract, is the definition. Again, and when you go to the examples, you're going to see that, for example, in the homework, you just apply the abstract concepts to these special cases, and then if it's either satisfying, it's either a yes or no question. So given something, is it a group or not? It's a yes or no question. Is it what's the map? Is it bijective or not? It's yes or no question, and so on and so forth. Today, inshallah, we're gonna again go up the hierarchy level to a more what's the word? To a higher level of structure. We're talking about vector spaces. Let's start as usual with a recap of what we discussed last time. So again, just to remind yourselves, for those of you who are in doubt, this is a robotics course, okay? So far there's no robots, and again, that's the whole idea of going up, trying to abstract the ideas and the concepts we're talking about. And this is just a look ahead about when we go to these complicated robotic systems, they're going to have a configuration space. I'm going to be talking about that in details. The configuration space of these advanced robots, even the simplest one, which is just a pendulum, they don't have the Rn structure. You cannot do them linearly. We cannot use them. We cannot represent them linearly, most of them. We cannot do linear algebra on them unless we do it in a structure, unless we exploit the structure that's already inherent in these mechanical systems. So just keep that in mind so that at least you have a motivation and don't fall along the way when in the deep mathematics that we're going to be covering. We said, okay, structures or spaces, they have some underlying structure beneath them. A set has no structure. We talked about the group, which has an additional structure. It's not just a set, it's a set plus some operation. Today we're going to be talking about vector spaces, and this is the level that you all are at with your linear algebra background. You all know what a vector space is, but today I'm going to introduce to you differently, and you're going to see what do we mean by all of this extra structure, and you're going to appreciate hopefully today a little bit what we've been doing. A recap, so a map between sets, what we discussed last time. So at the most basic level, a set A and a set B, a map between them, F, that maps elements in A to elements in B, again, would be represented by this standard notation. We would call A the domain of the map F, we would call B the codomain or the target of the map F. And then we saw that the map can either be surjective, either can be injective, or it can be both or neither. Okay. The inverse of the map, when we introduced the composition of maps, and then we said we can, if there's some map that when you compose it with a map F, such that you always get the identity, whether from right or left, whether you compose F inverse, F with this symbol, F, what we call the inverse of F. So F inverse with F, you get the identity, or compose F with F inverse, you get also the identity. Then this would, F inverse is called the inverse of this map F, and it essentially means that the sets A and B, if such bijection exists, and there is such inverse exists, this means that A and B are the same. So at a set theoretic level, they are the same. I can go back and forth between these two. Then we talked about groups, and we said the group is a set plus more structure, and this structure came into the form of some binary operation. And this binary operation or this map, satisfied some conditions. The first one is that it was associative. The second one, that there exists an identity element. And the third one, that there exists an inverse element, such that when we compose or when we operate between any element G and this inverse or this element that's also related to this element G, we always get the identity, okay? And we give some examples on that, and then we said that if there's a fourth condition on these two pairs, on this pair of a set and the operation, we call this abelian if we have this commutative property. And sometimes this is just called a commutative group. Okay, so commutative group, abelian group are two names for the same thing. Just a correction for something I mentioned incorrectly last time. I said that if something is not abelian, then it's called a non-abelian. Then I said it's non-abelian. I mentioned the term non-abelian, and some people ask about what does a non-abelian group mean. And I incorrectly said that a non-abelian would satisfy for all elements in it the fact that A commuted with B does not equal B commuted with A. The term non-abelian is completely redundant, because if something is not abelian, that's the normal group. So we don't have something called a group, abelian group, and a non-abelian group. It's just either a group if it satisfies these three conditions. If it satisfies also the fourth one, we call it an abelian group, and that's it. Okay, so this is just a correction of what I mentioned last time. I didn't check whether abelian was related to someone famous in math or not, but again, I don't know. That was a homework of someone. It is. Okay, so someone famous. Okay, that's called abelian. I don't know this guy in person, but again, it's interesting to look at it. Now let's go again. So this is the drill. We introduce new sets, new spaces. We look at the maps between them, and then we try to see whether these maps, they preserve or they respect this underlying structure or not. Let's do the same with groups. This is a mouthful, but again, if you read it at your own pace, you're going to find it's exactly the same what we did with sets. I'm going to give you two groups now. The first group called G with this, let's go back. The first group is called G with this operation called plus with a circle. That's just the name of the map, okay, abstractly. And I'm going to give you another group H with another operation, okay? And now, if there exists a map, okay, the map is called rho from G to H that satisfies this property. What this property is saying is the following. If I take any two elements in G, okay, so the first case group, and then I act between them with the operation that corresponds to G. So A and B belong in G. So I have to operate between them with something, okay, that the operation that corresponds to G. What is the element that I get? Which space I'm in now? I'm still in G. Then when I act with rho, when rho eats this new element, where do I go? I go to H, exactly. I go to something in H. I get the same result. I reach the same element in H if I would have eaten, okay, A first by rho and eaten B by rho, and then took the result with the operation with H. Okay. If the map satisfies this, we call this map a group homomorphism, just a name. Okay. This is exactly the same as a map between sets, right? But now with extra structure. Why do we need this extra condition or this extra structure? Because a group itself is not just a set, it has this extra structure. Yes?
Like this, the first part is equal to rho A, the operation B, not like separated. Is it like valid?
No, it's not valid. It's not valid because rho can act on something, can eat something where? Can eat something where? In G. A with this operation B, is it even valid? No, right? Because A is in G, B is in G. This operation needs to operate on something in H, exactly. Okay. So the nice thing about this way is there's only one way to write it. There's no other way, right? Because of how we define the maps here. Okay. If rho is also a bijection, so this is an extra condition. If it's a group homomorphism and it's also a bijection, again, you know what the bijection now means. It's just a bijective map. Then we call rho a group isomorphism. If there exists some group isomorphism, then we say that G and H, okay? Or in other words, the group G with its operation plus and the group H with its operation circle times, they are isomorphic to each other. What does isomorphic mean? It means essentially they are the same as groups. Okay? Whatever you can do with this guy, I can do it with that guy and vice versa, because I can go back and forth. Okay? This is exactly the same what we had with bijective maps between sets. Okay? The two sets are the same, and there is no extra information. Whatever I can do with the first set, I can do with the second set, and vice versa. Okay. If we have two sets, now that's a question to you. If we have two sets that are isomorphic as groups, Does this imply that they are isomorphic as sets? Yes, right? Because I already have a bijection between them. Okay. If I have a map, or if I have two sets that are isomorphic as sets, does that imply that they are isomorphic as groups? No. Okay. And if I have two sets that are isomorphic to each other with some operations, and then I replace this operation by another operation, I don't know, like a times circle with a cross circle, does this imply that these two are isomorphic as groups? No. You see, so this is very specific to the choice of G, to this and its operation, and H and its operation. Let's look at some examples. This is a map, exponential map, all familiar with. It maps R to R plus, okay? It takes a T, any number in the real numbers, and it gives the exponential of that number. The exponential only maps to R plus, right? So you cannot get an exponential and get a negative number. That's why we don't map to R. If I'm only focusing on this map, I define it like this. I only reach the R plus. And this is a group isomorphism between these two groups, the one in green and the one in purple. The one in green is the R with the standard plus that you're all familiar with. And this is the standard multiplication that you're all familiar with. I give you two positive, okay, real numbers. You can multiply them by each other. You get a positive real number. Because of this property, this is a property, just like a property of exponentials. You either know it or don't know it, okay? It's just something that's true. If you take the exponential of any two numbers, it is exactly the same as taking the exponential of the first one, multiplied the exponential of the second one, okay? So the exponential map between these two groups is a group isomorphism. And this means that whatever I do with this group, I can do it with that group because it's essentially the same structure. This map, the determinant between GL and R, what was GL and R for? General linear group. What does it compose of? Sets. It's a set of what? What's inside of it? Invertible matrices, exactly. So it would always map. So if it's invertible, if we only focus on invertible matrices, this means that we're going to be mapping to the real numbers, but we can never get the real number. What? Which number we cannot get? The zero, right? That's why this notation means that it's R minus, or we remove from it, okay, we extract from it the zero, okay? So it's R up to the zero. We don't take the zero into account. So this is the set number. So this is just the name of a set. This is the name of a set. This is a map that takes any matrix. You know how the determinant works, right? It works not only for 2D and 3D. You know the 2D, of course, formula AB minus CD, okay? So this is just the 2D, the 3D version. You can do it for ND, okay? There's a standard formula for that. You might not know it by heart. But for any matrix A, for any n by n matrix A that's invertible, I can calculate the determinant in the normal way that you know. I'm not going to be discussing it. But this is a group homomorphism between these two groups, between GL and R with the standard matrix multiplication that you're familiar with. Okay? So determinant of A multiplied by B, matrix multiplication, is equal to the determinant of A alone. What the determinant of A is a real number, right? So you see now that this is multiplied as in scalar multiplication by the determinant of B. Okay? And this is a group homomorphism. Now a question, why isn't this a group isomorphism? Think about it for a moment. So for this to be an isomorphism, so first of all, it's a group homomorphism. So because it has this property. What else do we need to make sure? What else do we need to check? For this to be a group isomorphism, it has to be bijective. What are the conditions for this map to be bijective? It has to be injective and it has to be surjective. Is this map surjective? Are you sure? Yes. I can get positive determinants, I can negative determinants. So I can hit the whole real, I can hit everywhere in this set. Is it injective? No. Why? I can give you two matrices that would give you the same determinant. So I cannot go back and forth, right? And it also makes sense. If I give you, for example, a 3x3 matrix that has 9 numbers, and you tell me I can represent it in one number, makes sense that they are not one-to-one, right? I cannot take 9 numbers and the information that they have inside and give you just one number, okay? It doesn't make sense, okay, logically. So this is why this is just a group homomorphism and not a group isomorphism. Clear? Okay. Abstract concept, maps between groups, examples, and these are two just examples that will appear later. Now let's go to vector spaces. Okay. This is the part that you're all familiar with. Okay, this is where I'm gonna break your pinch your bubbles. Okay, this is the place where you're all familiar. This is Rn that you all love. I'm gonna destroy it. Okay, so just let's see. First, vector spaces, just as an abstract note. We're gonna be dealing with vector spaces. Another name for vector spaces is linear spaces. Okay, everything we're gonna be doing in this course, between quotes, is non-linear spaces. Okay, there's nothing called a nonlinear space. There's no definition for what a nonlinear space is. But again, if you took any course on linear control and you dealt with nonlinear control, there's more like there's some higher level of whatever. Okay, so there's more tools, more advanced in some sense. The same here. So vector spaces are linear. Everything is any linear algebra. This is your bread and butter and what you like the most and what you think. Okay, this is what the world really needs. This is not what this course is about. But at least let's understand vector spaces in this abstract sense. We're not going to be considering vector spaces as Rn. If I give you any vector space, you can represent it in Rn, but we're not going to be thinking in terms of vector spaces as Rn. In other words, when I say a vector, what is the first thing that comes to your mind? Magnitude and direction. Okay, ugly, very ugly. Sorry, Tarek. Okay, but okay, magnitude and direction. Or what else? Just some numbers written in some form, right? When I say a matrix, what comes into your mind? Rows and columns, right? That's it. So this is what you come in mind. From now on, at least when you're inside of this row, when you're studying this course, vectors are something else. A vector is just an element of a vector space. So what is a vector space? The vector space is a triplet. It's three things. It's a set, some operation, and some other operation. Okay. Of course, these two operations, again, you're going to see that they're going to satisfy some properties, okay, together and separately. And this vector space is not just a set of n tuples. They're not just a collection of stuff that are written on one after the other in a column vector or whatever. But first, before defining what a vector space is, we need to define what a field is. Because usually a vector space is over a field. Sometimes you forget about this field, you just assume it's something. We're going to be discussing about it because it's very standard. But again, at least formally you need to say what a field is before saying what a vector space is. What is a field? Again, it's more than just a group. A field, okay, sometimes it's known as an algebraic field. Whenever I say a definition, between parentheses, something is, then the standard name for it is just a field. But sometimes if you want to be specific what type of field this is, sometimes people call it an algebraic field. So this is what this notation means. So a field is a triple, K, and the plus and the times. When I say plus and times, you immediately get something into mind. But I haven't said what these are yet. So the plus and the times, okay, are two maps, okay, that eat two elements from K, that go also to K. And they satisfy the following properties. K and plus alone, if you look at K and plus alone, they are an abelian group. Okay? If you don't remember what an abelian group is, this is what it means. Okay? They satisfy associativity that has an inverse element, and they have an identity element, there's an inverse element, and they're commutative. Exactly. You see here the inverse element of this group, we called it 0. This is just the name of this identity element. This is just the identity element of this group K plus. In the previous slide, if I give you some G and some operation, we call the identity element E. Okay. Whenever I say the general linear group, you always come into mind what's the identity element of it? The identity matrix, right? So some sort of 1, 1, 1, 1, 1, 1, 1 up to n, and then you have zeros everywhere. So this is what comes in mind of the identity element. So the identity element of this group, we call it the 0. Okay. So K and plus are an abelian group together. K, but we remove from it the 0, this identity element, and we look at this other operation, the times, is another abelian group. Okay. So these are the two conditions that we have. K and plus is an abelian group, and K, but we remove the 0 from it, and this multiplication is also an abelian group. But now you see, is a field just a collection of two independent groups? No, there's another condition, okay, that they should satisfy together. You see, now we're going to be coupling these two. They will be going to be related to each other, the plus and the times. And such that A plus B multiplied by C is equal to A multiplied by C first plus B multiplied by C. Of course, everything here is familiar to you because this is the R that you're all familiar with. Okay. The R, if it's just a set, then you just have like a bag and just real numbers inside. If it's a group, then you have R plus, right? You take two numbers and you plus them together and you do stuff with it. If it's a field, then you're also talking about scalar multiplication, right? You can multiply two real numbers. Every real number, you can think of it as there's an inverse. There's an additive inverse of it. What is the additive inverse of 1? -1. What is the additive inverse of 2.1? -2.1. What is the multiplicative inverse of 2? 1/2. Half. What is the multiplicative inverse of 3? 1/3, and so on. What is the multiplicative inverse of -1? -1. -1 over -1 is -1, and so on. Okay, so you know how it works. So R and plus and the normal plus and the normal times that you know R is a field. The rational numbers with the times and the plus, with the times and the plus is also a field. The complex numbers with the standard plus and the standard times is also a field, but not the integer numbers. Integer numbers with the standard plus and the standard multiplication is not a field. Does anyone know which condition out of these doesn't satisfy? Think about it for a moment. The 0. So the 0 in the integers is not there. Again, the inverse of the multiplicative inverse of an integer. For example, 2. What is the multiplicative inverse of 2? It is half. Is half part of Z? No, that's why it's not a field. Okay. So that's why R is a field, but Z is not a field. Okay. So this is just an example on the side. Usually, fields are either real numbers or complex numbers. We don't think of, again, unless you're taking a course in mathematics, for us in robotics or at least in control, we talk about vector spaces over fields, whether they are real fields, okay, or complex fields. And even most of the time, all the linear algebra you know is vector spaces over the reals. Okay, but at least just formally, you know now what a field is. Now, what is a vector space? The vector space over a field, and usually if we mean this is just an R, the standard multiplication with the standard multiplication and the standard addition, we just even forget about it. We sometimes call this an R vector space, or just it's a real vector space, and that's it. Okay. So a vector space is a triplet. V and some operation that we call vector addition and another operation that we call scalar multiplication. Okay. These are the conditions that we have. Plus, so this vector addition takes two elements of V and gives you another element in V. The scalar multiplication, the circ times, takes one element of the field of K and one element of V and gives you a V. They should satisfy some rules, of course. The first one is that the V and the plus is an abelian group. The second one is that the scalar multiplication is an action of the field on this group. If you don't know what an action is, it's just what satisfies these properties. Again, you just have some extra properties we need to satisfy. Okay, you can read them at your own pace, and you're going to have something in the homework to practice them. Okay, simply what a vector space is just a triplet, okay, with some conditions on the plus, some conditions on the multiplication. Okay, it's related to some field. Okay, so you can imagine that we have both of these operations that we're going to be all over the place. The conditions will have all of these. You see, this is the times, this is the plus, This is the small times, this is the small plus, okay? So the small times and the small plus belong to the field. The big times and the big, okay, sorry, the big times and the big plus belong to the vector field, and so on. You're gonna have just a collection of these, and this is what makes a vector space. Any element of this vector space is called what? A vector. That's it. So if I ask you from now on, inside of this room, at least until you get comfortable with it, what is a vector? An element of a vector space. That's it. What is a vector space? It's a space of vectors. Okay. It's and if I tell you what is the vector, if I tell you a V, what is the vector space V, you cannot answer that. You must tell me what is its corresponding scalar multiplication and what's corresponding vector addition. Example, Rn. Rn is just an example of what a vector space is. And the corresponding field is the real numbers, the standard plus that you all love, the standard multiplication that you all know, and this is the field. What is the vector addition here? How is it defined? Okay, first let's write it down. Let's see how I can annotate this side. Where? But the way I want to annotate on this. Yeah, there it is. Yes, that's right. Yeah, that's it. So if I give you, let's say, R3. Let's focus on R3 just for simplicity. Okay, is R3 with this vector addition and this scalar multiplication a vector space? Let's check. Okay, what do you mean by R3? Okay, I'm gonna write it in the way that you're comfortable with. So it's just some x1, x2, and x3 like that, or like that. Does it make a difference? Okay. What is the vector addition? How is it defined? So the vector addition between this vector and this other vector, how is it defined? I take x1 alone, okay, because it's one of the real numbers, and then I add it to y1. You see here what happened? What did we use here? We use this addition of the field. We do not use the addition. We cannot. They're not the same. Of course, for you in your mind, you don't write it this way. Okay? You just think of the plus as you do it by, again, you override the operator in your mind. But if you're writing a program, for example, you need to define what this operation is and what that operation does. So that's why we're being too formal here. We don't write this, but so that you know what we're talking about. And here we have the x2 plus the y2, and then we have here the x3 plus the y3. How is the scalar multiplication defined? So this guy. If I give you x1 and x2 and x3, what does this map between from where to where? It eats k times v, and it sends you to v. So it should take some element lambda, some scalar from the k, and the k here is a real number, so lambda belongs to this space. And then I multiply them together. How do we define this one? I take lambda multiplied x1, and this is the normal multiplication we're all familiar with. I take lambda multiplied by x2, and I take lambda multiplied by x3. The rest of the conditions of everything that we're talking about, take your own pace and try to prove that they are all true for all Rn that you're all familiar with. Could you raise your voice? For the field, yes. These two together should be abelian, and these two should be abelian. And there's another condition that these two should be distributive. Yes? The multiplication and the plus, they had some extra conditions together. We did not go through them, okay? This is what was just summarized by that it's an action of a group, okay? We did not say exactly what that means, but it just satisfies these extra conditions. Okay? It's not an abelian group. No, we don't require that. Question?
So, based on the definition now, the plus for the vector space is different from the plus of the field.
That's right.
Then in this case scenario, seems like we're defining the plus of the vector space in terms of the plus in the field.
That's right. Because, why are we doing that? Because Rn is the Cartesian product of R plus R plus R, right? So that's why they're intertwined.
So that means that, say for example, assuming we have a new vector space.
Yes.
That moves from a vector to a conventional matrix, for example.
Okay.
In such a case scenario, we would have additional operations.
Yes. You have to define this operation. Exactly. You have, that's why this is the definition of an abstract vector space. You have to say what this is and what this is. And if they satisfy all of the conditions that we had, we call this triplet a vector space. And you're going to see some examples of some stuff that are just right now, okay, that are vector spaces, but you never thought of elements inside of them as vectors. I'm going to give you an example. Just 10 minutes, 20 minutes maybe. Okay. Another question. There was a question here, I think. The lambda is, okay, so this is the just, if you remember this guy. So this operation, we said, what happened? Press something. The X, yeah, okay, go to X. So this guy was a map from K to V to R to V, which means that it takes an element from here and an element from there, and it will map it to a new element that's defined like this. So what I'm writing here is how is it defined? Okay. And this is something that you learned in elementary linear algebra, right? If I give you a number, half, and I tell you multiply it by a vector 1, 2, 3, what do? You take 1 divided by half, multiplied by half, 2 divided by half, 3 divided by half. What is this? What is this operation? This scalar multiplication. What is the multiplication that you do for every entry? It's this multiplication, right? Maps, okay, and this is something that you need to be always formal with. And this is something I hope, if you only get out of this out of this course with this for the rest of your lives, even if you're not going to do control, if you're not going to do robotics, I would really appreciate it, is whenever you have a map, always know what this map from where to, okay? That's it. This would be just enough. The very good question. Can you replace lambda with a vector? So you're thinking of a dot product and a vector product. A vector space, does a vector space have a dot product? No. Does a vector space have a vector product? That's it. Of Rn. That's the problem of Rn. Rn has more than what you just need. It has vector product, it has a dot product, it has a manifold structure, it has a group structure, it has a Lie group structure, it has everything. That's why when you're working with Rn, everything is possible, everything is nice, everything is easy. Okay? That's not the case with the spaces we're going to be thinking about. Okay?
From V, x1, x2, x3.
Yes.
Should this be different elements? Maybe it's a different element. I mean, now
No.
lambda is just one scalar.
Yes. This should happen for this. This is defined for any scalar.
It's x1 by the vector, then x2 by the vector, then x3 by the vector.
No, sorry. So you mean in this case? This case is just another way to writing it this way. So this guy is just another way of writing this guy, right? I can write vectors. I can write elements of Rn either like this or like that. It's another way to write a vector, right? Exactly. That's why vectors are just elements of vector spaces. They're not how you write them. They're not how you put them on top of each other, right? It's not just what a column is what's called a vector. Everything you can do here, you can do it like this. Okay. Any other questions?
So then you have statements across the line, like
This one? Okay.
verify that R or whatever is defined as R in this scenario is the Q.
Yeah.
Then we find that Rn itself.
That's right. Exactly. 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 Okay. These are just, this is what you already know. Okay, so this is the vector addition you already know. The vector multiplication you already, sorry, the scalar multiplication between a vector and a scalar that you already know. And this is the standard multiplication, the standard, sorry, standard addition, standard multiplication that you already know. That's why I'm not defining them, okay? Later on, when we have something more complicated, we have to define these. This is what's coming up. Rn, okay, the vector space Rn, not the set, okay? Not, so again, Rn can be a set, but when we talk about the Rn vector space, we means everything on top with it that comes. It's usually called the n-dimensional Euclidean space. Okay? So when you're talking about Euclidean space, you want to talk about dynamics on Euclidean space, x dot is equal to ax plus bu, and you say x belongs to Rn, you're talking about this Rn. You're not talking about the set. Okay? Because you're doing plus, and you're doing times, and you're doing stuff, and you're doing matrix multiplication, blah, blah, blah. Okay? Yeah.
I said the vector space as this expression of the three values, we can just refer to it as Rn.
Exactly. This is usually what people do, right? I don't always need to tell you it's an R vector space and it comes with vector addition and vector multiplication, blah, 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 right? It's just assumed. It's like you learn it once in your life and you don't always need to remember, just to move on, right? This is the same. But if you want to ask, what is the underlying field of Rn as a vector spaces? This is the vector field and so on. Okay, this is because we're building this up. We need to be very formally so that you can see the difference between all of these. In practice, if you know it once, you don't need to always remind yourself and write. Okay, what can be written in a line, you can write it in a page because you need to specify all of that. Okay, and usually it's also specified sometimes in Word, right? Now let's look at exactly the same drill that we did between sets, groups, and vector spaces. When we have sets, we said that we can define maps between them. Okay? And if these maps, they can go back and forth between these two sets. If you have a map that identifies or makes two sets isomorphic to each other, we call this a bijection. When we had the group, okay, some group and its own operation, we said then we have a map that respects the group of where it comes from and where it goes to, then we call this a group homomorphism. And if in addition we can go back and forth between these two groups and they are equal, we call this a group isomorphism. The same will happen with vector spaces. If I give you a vector space Rn and another vector space Rm, what is the map that goes from Rn to Rm? We call it a linear map. Okay? So linear maps, they respect the vector space structure of whatever vector space that you have. So you see, this is the type of map that would respect it. But again, if we can go back and forth between we cannot go back and forth between Rn and Rm, but you know that. But if I have Rn and Rn, okay, and I have a linear map that maps them, I can go back and forth. So it has to be invertible. You all know that. But again, in our language, this is a bijection between two vector spaces. In this case, we're going to be called linear isomorphisms. We're going to be defining what linear maps are and what linear isomorphisms are now on the board. Okay, so this is the part we're going to stop with the slides. Let's continue with the writing. Any question before we move on? Okay, so pens and papers or tablets, whatever. Whiteboard. Okay, let's see. Okay, so linear maps. Okay. Let the triple V plus and times and W plus and times be vector spaces over the same field K. Okay. And whenever I say the same field K here, you know that K will come with its own standard, okay, addition and its own standard multiplication. Okay. You see now here that W comes with different vectors additions and different scalar multiplication than that one. That's why we give them different symbols. We say that F the map that goes from V to W is a linear map. So this is the definition of what a linear map is. So this is a linear map if for all V1 and V2 in V, which means that if I take any two random elements in V, in the vector space V, okay, let's write this properly. And all lambda in K, we have the following. We have that F of lambda multiplied by V1 plus V2 is equal to lambda multiplied by F of V1 plus F of V2. Take a look at it because it's very, very annoyingly written. It's a lot. If you look at it, if you try to read it once, it will be clear. And it's also familiar. You all know, you've also all seen it somewhere before. If we have a map, okay, F that satisfies this property, okay, we call this a linear map, okay, because it respects, okay, that when we go from vector space V to vector space W, okay, this map, okay, will respect this structure of V and W. Okay? And there's another way, usually that you've probably seen this before, and probably you've seen it written in this way. So a linear map, usually you're all familiar of it in this way. It's a map that would satisfy F of lambda V1 plus V2 is equal to lambda F of V1 plus F of V2. Oops. No. Let's see. Okay. Who never saw this before? Okay, we've all seen this before. So you now understand what this means, right? But of course, this is a notation overkill, right? Because I'm giving a new operation for the V, and I'm giving a new operation for the W, and I'm giving new operation for the field, and so on and so forth. And that's why if you understand what it means to be a vector space, and you understand really what is the underlying structure, I don't need to introduce, I can use the plus to identify addition between numbers, addition between vectors, addition between matrices, and so on. Okay? Multiplication, you know what multiplication is. I don't even need to write, I just write the symbol next to each other. Okay? If I write lambda V1, you already know that V1 will be a tuple of numbers. I'm going to multiply the lambda by each one of these. So you do all of this computation in your mind, right? But if you're writing a computer code, you need to tell the computer that this is a scalar and this is a vector and so on and so forth. Okay. So this is the abstract correct way of thinking about it. Okay. But in practice, we don't really do it like that. But at least you need to look at it once in this way so that you can appreciate all of the implicit computation you do in your mind when you're working with linear algebra. Okay. Yes. Lambda is in K. Okay, so that's why I write it like this. So lambda is in K. That's why you see here when we use the lambda, with the V1, we use the scalar multiplication of the V that takes K, an element of K and an element of V. When we use the lambda here, okay, because it's, you see, we had one condition here. It has to be the same field K. So this is a vector space over K, and this is a vector space over K, which means that this is a map from K times V to V, while, did I write? No, this is this one, okay? This is not correct. So this is the one here, and this is a map from K times W to W. Okay? Clear? Last thing is that, okay, another extra condition if this map F between the vector space V and W is also a bijection, what do we call it? We don't call it a linear map, we call it a linear isomorphism. That's it. Which means that as vector spaces, I can go back and forth between these two. Okay. Let's again look at an example. At the page. The pages here are saved. So even if you didn't write it down, you can come at the end and you can take snapshots with your camera. Okay. So an example. Okay. If I have the vector space Rn along with the plus and the scalar multiplication that you all know and love, and another vector space Rm with the times and the times and the plus are the same. Okay, but here I give you an n tuple, and then you do the plus n times. Here you do the plus m times. Okay, it's the same. You don't even think about it. But that's why there are two operations. We write them with the same symbol. Then the space of a linear map would be some A that would map you from Rn to Rm. Okay, and usually you think of A as being some sort of A1 up to AN. Is that, yeah? And here some up to, sorry, A11 up to A1n, and you have here AM1 up to AMN. Okay, this is what a linear map is, right? And the how is this map defined? Okay, so the map F that eats a V, okay, and gives you an element in W, if this is V and this is W, so yeah. This one eats from Rn to Rm, okay? So this is what you always think of as an M times N matrix. So it has M rows, correct? And N columns, yeah, that's correct, okay? And F of V, which is this two together, how after they go to Rm, they are defined as A11 multiplied by V1 plus A12 multiplied by V2 up to A1n multiplied by Vn. And then you have here AM1 multiplied by V1, blah, 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 blah. You know how it goes. But you see, so what you do as the matrix operation, the matrix multiplication, is just the definition of this map F that goes from these two vector spaces, capital V and capital W. There's a question at the back. Yes?
So if we find the Rn as a row vector.
Okay.
As a map.
Yeah.
We're defining the map between Rn and to Rm. The operation of the A itself. How we define the map. This is the definition of the map. I'm gonna put this in the homework. So you have to do it at your own pace, so that it all clicks together. Don't try it at it right now, because I want to confuse you even more. Okay, for now. Okay, just wait. Okay, you're gonna do this in the homework. So this is part of the homework. Okay. That's a very good question. Very good question. What does A belong to? What is the set that A lives in? We're talking about a map now, right? So what you're talking about is a set of maps. This set of maps, okay, which is actually the next part, between two vector spaces, okay, has different names, different symbols. Sometimes people call it L between V and W. I think sometimes, let me see if they put the semicolon or not. Yeah, it's written like this. So A Annoying. So, no, no, it's there. That's not there. So A lives in here. This is the set. So how is this defined? How is this set defined? Let's define it. And we're going to write like this. So this is defined as all F's such that F is a map from V to W, but it's also linear. So this is just a notation to identify that this is a linear map. In other words, it's just the set of all linear maps. Okay. If the vector spaces you're thinking about are Rn and Rm, this set, you can think of it as Rm times n. Okay. But again, you're all of your like comfort zone is here. Everything here is just abstract because what we're doing here can be extended. What you're doing here cannot be extended to the spaces we're interested in. This is why we're doing this more complicated way. Question? We're defining a new set, exactly. We're defining the set of maps. This is something very new. And because we're defining the set of maps, we're not saying, it would take us a lot of time and a lot of formalities just to say, where does this F belong to? What is the bigger set? You know, when we define subset, we will say, okay, I have a subset that's a part of S and I put conditions on this. But what is the set of all maps that are linear and also non-linear? We haven't said what this is. That's why I leave this open, okay, without saying what it is. So again, L, V, L, brackets, V, semicolon, W is a set. If I select one of its elements in this set, I'm going to find it's a map F that would take me linearly from vector space V to vector space W.
Dealing with vector spaces.
Yes?
Or not describe it, but it's like we started with sets.
Yes. Yeah. More structure. More structure, yes.
More structure than sets with a set again.
Because a vector space is a set with operations. What is the operation here that this vector space has? We can define it. We can give it something that looks like this, and we can give it another operation that looks like this, and we can define them. We're going to have this in the homework. In other words, and this is the tricky part, the linear space, and this is something you can prove. It can take you a couple of pages. You can just take it from me from my word, and I can give you the reference to look at it at your own pace. Part of it will be in the homework, not everything. So it will be supplementary because it will take some time. But if you do it, you can show the following. You can show that if V is a vector space, and if W is another vector space with different operations, okay? They don't even need to be the same, but let's keep them for now like this. No. Again, the notation for fields is just an abuse of notation. But again, you either abuse the notation or make your life too complicated and formally. Again, this is your taste as a mathematician. Okay, we're engineers now, and we want to do control. Okay, if we write everything very formally, it will be too complicated. It will be formally correct. Anyone that comes at any point in the room will always understand what we're talking about. But again, it will be just an overkill in terms of notation. You're right. But these are vector spaces. I'm telling you that these are vector spaces. Okay, so you already know how this is defined and how this is defined. And if we have L of V W, which is what? The set of, this is defined as the set of all linear maps. They have to be linear between V and W. This set, I can make it into a vector space structure. If we give it some sort of plus and scalar multiplication that we haven't talked about. So LV and W, with these two operations, can be made into a vector space. Now that's the confusing part. This is in general for any vector space. Of course, they have to be finite dimension. Okay, you know what finite dimension is, so I'm not gonna formally prove what it is. We'll just take it at the intuitive level that you all know about. But let's say that this is Rn, for example, and this is Rm, for example. What do you think of these guys as what? R that would multiply. Okay, think of it this way. What are the linear maps that would multiply an n vector, make it into an m vector? M by n, right? So Rm times n has a vector space structure. So an element of a vector space structure is called a vector. So V in here is a vector, W here is a vector, and the map here that lives in this map, set of maps that goes from Rn to Rm is also a vector. In other words, what you know as a matrix is actually a vector equipped with the correct operations. And these operations, by the way, this one is just, if I give you a matrix A and a matrix B with the same dimensions, do you know how to add them together? This is this guy. If I give you one real number and another matrix, and I tell you multiply them together, do you know how to multiply them? This is this operation. So do they satisfy the properties of vector spaces? Yes. Okay. So is Rm times n or Rn times n is it a vector space structure? Yes. Any element from there, is it a vector? Yes.
Over the field R.
Over the field R. Okay, over R. And this is a vector space over R. Yes. And by R, I mean the plus and the times that you all, okay, are familiar with.
Can you like a formed structure from the two?
A is an element of this space, is an element of that set. It's a vector.
Can you structure?
If you take any A from this set, what do you get? You get a map from Rn to Rm. Isn't this exactly how you always think of matrices, right? A matrix can always map an Rn to Rm. How do I do that? How do I define this map? I do the matrix multiplication, row by column, row by column, row by column to get a number, row by column to get a number, row by column to get a number, and so on. Now let's confuse you even more. Usually, sometimes people, let's see where it is. Shall I say it or not? Okay, I'm not gonna say it this way. You have a question? Yeah. We can make it into a vector space if we give it the correct operations. In general, you mean? So we can have a vector space and a vector space, and we can map between them. And this map cannot, the set of maps cannot have a vector space structure? No, this is in general. You can always make this. You can always make the set of linear maps between two vector spaces into a vector space itself, abstractly. Okay. Any questions? Okay. Now, because we have this big set, which we called L of VW, okay? And every element in here is a map. If we have this big set, what can we look at? What can we look at? Subsets, right? Let's try to restrict a little bit. Let's define a subset from here. They are called endomorphisms, okay? So an endomorphism, okay, is a map F that goes from V to V, from V to itself, and is linear. Okay, so linear maps from V to V are called endomorphisms. Okay? So what are the linear maps in general from V to W between two different vector spaces. If I'm talking about the same vector spaces, okay, we call this an endomorphism. Of course, the map has to be linear. Why do we need the linear condition here? Because we're talking about at which level now? At vector spaces, right? That's why we want to have this additional condition on the maps. We would call let's see, an automorphism, okay, F between V and itself, and it's linear. We would call the map F an automorphism if F inverse is linear and also exists. In other words, we want F to be here what? A bijection, exactly. So if F is a linear map, we can go from V to itself, and it's also a bijection. We call this an automorphism. We can think of it this way. So we have here all elements, okay? We have here all elements that would map V from W. If we restrict ourselves to a subset here that goes from V to itself, so L of V to V, we call these the endomorphisms on V. So this is a bigger set, a smaller set than LVW. And inside of this set, we can restrict more by having automorphisms, exactly, on V, which are sets, so which are maps that can go back and forth to be V, okay? So they are also bijection. You're all familiar with all of these maps, okay? Now let's look at Rn times M. So if V is Rn and W is Rm, then we said that this map of V of linear spaces from V to W is what you know as R M times N. What do you think the endomorphisms are on Rn? What are the endomorphisms are on N? What are the linear square matrices exactly? Square matrices, which are N times N, they are the endomorphisms. What is an example of automorphisms on Rn? Yeah, invertible matrices. What was the name that we gave to the set of invertible matrices? So, vector space. You all agree? Vector space, right? How can you show that? Okay, you need to show it, right? You need to show that if I take two linear maps, okay, and I operate them together, okay, sorry, I do stuff with them together, I satisfy all of the vector space structure. Do I always have that between linear maps? Yes, you can always make the endomorphisms also into a vector space. The question is, think about it for a moment. Do automorphisms have a vector space structure? Okay, what does a vector space structure mean? It means that if I take an element A that's invertible, and I add to it an element B from this space that's also invertible. So this is a square matrix. This is a square matrix. You add them together. Is the determinant is the determinant not equal to 0 in general? No. You don't have that, right? The simplest case is to have A and minus A, right? You get a determinant of 0. So in general, you don't have that. So we don't have, GL and R does not have a vector space structure. What does it have? What kind of structure does this guy have? A group structure, right? This is what we discussed. What is the group operation? If I give you two invertible matrices and you multiply them together, do you get an invertible matrix? Does it have an identity element? Does it have an inverse element and so on? Yes. So this has a group, but not vector space. This has a vector space. Does it have a group structure? If I give you two n by n matrices and you multiply them together, Okay. Do you get another n by n matrix? Does it have a identity element? Yes. Does it have an inverse? In general, not. I can give you a matrix, an n by n matrix that doesn't have an inverse. So does this have a group structure? No. So conclusion, vector space, not group. Vector space, not group. Group, not vector space. Enough confusion? Okay. Question? Sorry? Themselves are not groups. That's a good question. We said that when we define vector spaces, we used some groups, right? We said that V, so for example, when we had the V and its own plus vector addition, we said that these together are a abelian group, but we had more structure than a group, right? We had more conditions on the relation between the plus and the secondary multiplication and so on. But V as a vector space comes with two operations. When we're talking about a group, it's only the set and one operation. So you see, that's why a vector space is not a group. Okay, it's more than just a group. It has more structure. Again, the term structure is very abstract. Okay, it's you understand what if I give you something that's structured and not structured, you know what it means. Okay, you can it's like it's an abstract concept, but mathematically it means that we have either more operations or more sets that are used to define it, and we can do more with it than what we can just do with groups. Okay, so again. So you've seen this before, but probably never thought about it. So you need to digest this a lot. Okay? We're going to be continuing on that. So this is only the first lecture on vector space theory. Next lecture, we're going to be continuing on that. People who don't come next lecture studying this material will suffer a lot. Okay, so you have some homework to do on Sunday, Monday, and Tuesday morning. Okay, I'm going to also post some homework, especially for this lecture. Okay, the homework will be for this lecture and Tuesday's lecture, but only solve the part for this part so that you can come prepared. Okay, any questions before we end? Okay, let me. Sorry?
Of course, this we are increasing vocabularies.
Oh, what I'm doing so far is destroying what you already know. So let's stop for now.